We going to start? I'll start.
Good morning, all, and thank you for joining us this Saturday morning for a tech talk on AI, video, IoT, and their applications in smart cities by Dr.Tinku Acharya. At the outset, I would like to welcome the speaker, and also I would like to extend a warm welcome to all the participants who have joined us, and also our ComSoc Execom member, Dr. Sanjeev Guru Gopinath, and also we have with us Chair Dr. Ganeshan, IEEE ComSoc Bangalore chapter. I would now request Dr. Ganeshan to share the opening remarks and formally have the tech talk kick-started. Ganeshan sir, over to you.
Thank you, Changapa sir. Good morning and warm welcome to everyone around the world. And this is our fourth or fifth technical talk for this year. As you all know, that the ComSoc is a very vibrant community in Bangalore, where we have a lot of participants from both academia as well as the industry. And today's speaker also is one of such kind, where he kindly agreed to share his knowledge with the student community and the professional community we have. The motto of IEEE is to bring the technology for the betterment of the humanity, right? So in that aspect, sharing knowledge to the students and other professionals is one of the ways you can improve the knowledge base in the country, right? And which in turn helps to improve the humanity in multiple aspects. And we are arranging technical talks in variety of topics. Like if you go to our ComSoc website, or if you read our newsletter, we will probably provide the link here in the chat box soon. You can look at the variety of topics that we have been discussing. Not only this year, you can look at the last year, like we have conducted about 50 plus events, variety of topics, workshops, hands-on workshop for students, long deep dive sessions like on 5G, like that. Then there is a talk on quantum communication. In fact, I can give you that next month we are arranging some talk on quantum technology also. So there we will be always giving you the cutting edge technology, but it is kind of given at a level where the students can appreciate, and at the same time the professionals also gain some knowledge. So can attend from the convenience of from their home, and it is free. So only thing we need to just register for the logistic purpose. Otherwise, all the 1 hour workshops or webinars are always free. So please attend, and please give your feedback at the end of the session, as well as you convey the word, pass on the word to your colleagues and friends and fellow students, faculty members, so that they also join and get benefited in this knowledge sharing sessions. And if you see that there is benefit in if you see there's a benefit in knowledge sharing session, please come forward in giving talks. I'm inviting to professionals as well as the faculty members who wants to share their knowledge. Please come forward and propose your topics. We will we'll see how we can accommodate in the schedule. With that short prelude, I invite you for the ComSoc lecture and invite you for the ComSoc Society. If you wish to become a member, please contact one of us. And for more details, you can look at our ComSoc website, or you can even write to me. We will provide the link for our ComSoc website as well as our last year newsletter, where you can get more details. Just the last note, I would just want to highlight that we have been adjudged in the Asia-Pac region best ComSoc chapter for the last 3 years in a sequence in a row. And 2021, we are also got the Year of the Award worldwide chapter award. So that kind of talks about the type of activities and the events that what we have conducted so far, and how what feedback we got from the attendants, and through that the evaluation has happened worldwide, and then we were adjudged as the best uh, mm, chapter of the year award was given to us in the last 2021 GlobeCom conference. Thank you. Over to you, Sanjeev.
Yeah, thanks, Gana. Good morning, everybody, and I welcome you to this very distinguished lecture on AI, video IoT, and their applications in smart cities. So it gives me a great pleasure to introduce the speaker today. Yeah, Gana, you say something?
No, you are fine. Please go ahead. Yeah.
All right, so it gives me great pleasure to introduce the speaker today, Dr. Tinku Acharya, who's a fellow of IEEE and founder of Videonetics. The credentials, uh, uh, the achievements of Dr. Acharya are so many that if I start to talk about all of them, it would require at least 15 minutes of time to talk about all of them. In fact, they are so many that they are heavier than the tails of a generalized Gaussian distribution. So it's quite a few. So let me just talk about just a little bit about Dr. Tinku Acharya, and then I'll hand over the stage to him so that we can utilize his time, and then most of the time is spent on the technical content. Dr. Tinku Acharya, simply put, is an inventor, entrepreneur, scientist, teacher, author, and an internationally acclaimed technologist. He is the founder and managing director of Videonetics Technology Private Limited, Kolkata, and also he's a visiting professor at the Indian Institute of Science in Bangalore. Dr. Acharya received his BSc honors in physics, BTech, and MTech in computer science from the University of Calcutta, and a PhD degree from computer science from this University of Central Florida in USA. He is a fellow of IEEE, INAE, IETE, and other institutions. So there are, as I said, several credentials for Dr. Acharya, and then I would probably skip those in the interest of time so that we can get to hear the technical content from the speaker directly. So once again, I extend a warm welcome to Dr. Acharya for taking his time to give this distinguished talk. So over to you, Dr. Acharya. Thank you.
Thank you. Thank you very much for the introduction. And I'm glad that I'm speaking in this communication society, talk. I remember, I gave the, 2011 or 12, that time, I gave a talk in IEEE, Communication Society, Bangalore. So that time I was invited and I spoke in a different topic. So this is my possibly the second lecture in this Bangalore chapter. So thank you very much for inviting. So, I like to keep it, interactive, and I'll share some of my experiences. So the topic is AI, artificial intelligence, video IoT, and their applications in smart cities. And what I'm going to do, possibly next half an hour, there are lots of myths around AI and IoT. So, so I like to, break those myths and give the very clear concept, where from it is coming, where it is going, and why we are today, what we are doing, what is the journey, so that, students, faculties, and researchers, they have a idea that how we came today, and what is influencing, this growth, and it will continue to grow, and what is coming in future. So with that essence, I'll give the talk, right? So let's start with artificial intelligence. So, before we speak about artificial intelligence, it is very important to understand what is intelligence all about. Now, we call certain people very intelligent, certain people not so intelligent. Why we say that? So intelligence essentially is ability to make the right decision, right? And intelligent people, they often make right decision, good decision. So, and the decision happens based on certain criteria. People do not just make a decision based on certain criteria, and using their prior knowledge or training, right? Based on their knowledge, based on their training, they make some decision. That decision could be good decision could be bad decision, but essentially decision making is an important aspect. So that is defined as the intelligence. And when we are talking about human being, the human intuition, it plays a very, very significant role to demonstrate the ability of making decisions. So intuition is an integral part of natural intelligence, and this natural intelligence or intuition happens because of their lifetime experience. One have and an acquisition of knowledge since our birth, right? So we are acquiring lots of knowledges. We are experiencing many things. We are seeing many patterns in our life. We are seeing the patterns in people or in the nature. So essentially, based on those patterns, when you go to a medical doctor, based on the previous case histories or his knowledge, the pattern, he can quickly make a diagnosis, possibilities or that, etc. So pattern recognition, recognizing the patterns based on the previous data or previous experience is very, very important. So that's why modern psychologists, they define the intuition, human intuition. Modern psychology characterize it by pattern recognition. So that's why in computer science or in our domain, pattern recognition is an important subject. So unless we master in the pattern recognition, it is very difficult to understand the nuances of artificial intelligence. So essentially, to summarize in a very simple language, intelligence is the ability to make the decisions based on our prior knowledge or certain criteria. And human intuition plays an important role into this intelligence. And intuition happens based on the lifelong experience and acquisition of knowledge since the birth. And that lifelong, experience or acquisition knowledge, it is gathered based on patterns, which we have, observed or experienced in our life. And pattern recognition is an important aspect of the artificial intelligence today. So, then what is artificial intelligence? So artificial intelligence is the machine learning techniques. What it does, it essentially attempts to computationally model the world around us, right? So and that is the criteria to demonstrate the notion of artificial intelligence, right? So machine learning techniques, how machine learns. Again, pattern recognition comes into the picture, and based on that, we computationally model the world around us, and based on that modeling, we make decisions. So essentially, we are asking a machine to make the decision, computing element to make the decision. And pattern recognition plays a major role in this. And artificial neural network, there are many aspects of artificial intelligence. When I started my research in studies in early 80s, in the domain of artificial intelligence, artificial intelligence basic tools and the concepts and the theory was different, and it evolved, right? There are many aspects: statistical pattern recognition, predicate logic, predicate calculus, then heuristic search techniques. If you remember the faculties early days 80s, there was only one book on artificial intelligence. That was the based on heuristic search techniques. Okay, so Niels J. Nielsen, that is the author of the book. So from then, it evolved a long way, and today's world, artificial neural network became very popular. Why artificial neural network became very popular and what made it possible to do it today, and it has aspect of the hardware and VLSI and advent of the computing that I'll cover in future few slides, right? So since it is not possible in a short time to cover all aspects of artificial intelligence, so I'll be covering mostly artificial neural network because most of the people these days, they are focusing in this domain. So artificial neural network, essentially the same thing, computationally attempt to mimic the learning capability of biological neural system. Okay. So using a computational architecture. So in the computational architecture, how we can mimic the biological neural system, our brain, how our brain thinks, how our brain makes a decision. So that mimicking into the computational architecture, that foundation is provided by artificial neural network. So let me go back a little bit. As I said, I am working on this, since my graduate studies live in early 80s, right? So if we go back to the little history, these days young kids, they think the artificial neural network is happening today or artificial intelligence is a subject today. No, artificial intelligence, this topic, it is more than 7 decades old, almost 8 decades, almost 80 years. Many people have contributed. Based on that contribution, we are where we are today. So Alan Turing, he is essentially the founding figure or father of modern computer science and artificial intelligence. So he was an English professor, mathematician, and he was a theoretical biologist. He is the first one who raised the question, can machine think? So, and based on that, he did some mathematical modeling. And with that, he has shown in early days, in 40s, that yes, machine can think. And 1950, he did a test. It is called Turing test. And based on that, there is a popular theory called Turing machine. Every computer scientist, who have done the research and development and studied computer science, they know Turing machine is the foundation of computing today. Turing machine is the foundation of design and analysis of the algorithms today. Turing machine is the foundation of all the programming languages today. Turing machine is the foundation even the parallel computing today. So without Turing machine, we wouldn't come here where we are today, right? So essentially, Professor Alan Matheson Turing, he is the father of theoretical computer science and artificial intelligence. But more than that, what I like to specially recognize here that, today we are seeing the artificial intelligence techniques in various fields, right? And, in technology, in various commercial and social aspects, it is being utilized. But to me, the most significant contribution of Professor Turing, that was during the Second World War. He is the first one who gave the concept of cryptanalysis, cryptographic theory, cryptanalysis. So during the Second World War time, based on his cryptanalysis techniques, when Germans, were sending the secret messages, he could decipher that. And based on that deciphering those messages, they could take preemptive actions, these friendly, front during the Second World War, they took the preemptive actions, and based on that preemptive actions, could frustrate the Germans, right? And the war ended, 2 years ago, and it saved 2 years. And because of war could end 2 years, war was shortened by 2 years, it could save more than 14 million lives. 140 crore lives was saved. If that Second World War continued 2 more years, we could have lost 140 crore people, right? So this is a significant contribution in the history of human civilization. So that means artificial intelligence based cryptanalysis technique, it stopped World War, helped to stop World War well ahead of time and saved 150 crore people's life. To me, in the history of civilization and the history of computing, that is very, very significant. So that was possibly the first application of artificial intelligence. With this little theory, little history, let me proceed. After that, his able colleagues and many, many great computer scientists advanced the subject. One of them is, I'll tell those names. All of you, most of you, people who particularly, since you are in the part of, IEEE Communication Society, so the Professor Claude Shannon, he was the father of communication, right? In 40s, for 1946 precisely, he first gave the theory of communication, theory of entropy, how to measure the information. Okay, so he's the father figure of theory of communication, and he gave the concept of entropy to measure, the information. So that's why you are doing information processing today. So Professor Shannon, McCarthy, Minsky, Rochester, these are all great computer scientists and thinkers that time. They first coined the terminology artificial intelligence in 1956 in a conference, in Dartmouth conference, summer 1956. So before that, people did not talk about artificial intelligence, but cryptanalysis, this technique, that technique, those are being first formally artificial intelligence terminology was coined by into this conference, mainly led by Professor Claude Shannon. So you can see all the great minds, father of computing, father of communication, these were the people who contributed, visionary people. Because of that, we are talking about artificial intelligence today. After that, Frank Rosenfeld, he first invented a perceptron, concept of perceptron in 1957. And since that, perceptron was the beginning of neural networks. So artificial neural network, it is not today's. From 50s it started. And Minsky advanced it more. And Professor Alan Turing, he did the Turing machine concept. And Minsky first time in 1962 developed an universal Turing machine. And he wrote his the book on perceptrons. That is a very significant book. And in 1970s, he gave the theory, society of mind theory, how mind works. So these are the foundations. Then lately, Professor Papert, he formally gave the concept of the artificial neural network and its mathematical formulation. 1979, Professor Fukushima, he first introduced the concept of new cognitron. The new cognitron is nothing but a multi-layered artificial neural network. Before that, our artificial neural network was simple. So neo-cognitron theory came based on the back propagation. There are many, many theories behind it. And that neo-cognitron, it was a multi-layered, not single-layered artificial neural network. And that is the foundation of deep learning technology today. So everywhere, these days, when I talk to the researchers, students, even the kids, everybody knows these days, deep learning. Okay. So the reason I wanted to present this slide, where from this deep learning came and what is the history behind it. So essentially this new cognitron theory by Professor Fukushima, that planted the seed of today's deep learning technology. Okay, and that is the latest artificial intelligence techniques and being adopted by the people. There are a lot of skeptics about deep learning. There are lots of skeptics about this theory, but there are lots of hopes also. So both the sides, there are lots of scientists against it and in favor of it. But whatever it is, deep learning is a big talk today, or artificial intelligence network, a very big talk today, and that is influencing the AI today. And why that is influencing AI today, why deep learning became applicable today, practical implementation possible today, I'll talk about it. It is not just the mathematical formulation, it is not just the theory. To bring it to the practice, the way computing and programming paradigm has evolved, understanding of that is also very, very important. So before I do that, let me give little background. As I promised in this talk, I'm not going to use too much mathematics or theory. I'll just tell stories so that people can comprehend, right? But one slide I have to use little math to give the background of artificial neural network. So, human brain. So human brain, it has billions of, cells, right? Those are called neurons. So the same concept of neuron, we can think about it. It's a mathematical relationship function, right? Looks like this. No? So x1 w1 plus x2 w2 and so on. So if you look at it, it is nothing but multiply and accumulate. What does accumulate means? That means we have two numbers, x1 and w1. Let's say x1 is an input, w is a weightage factor. We multiply that. Like that, there are many, many samples. Once we multiply and accumulate, that means add them together. So multiply and accumulate. And people, in the communication society, there are many signal processing people. And in the signal processing, all the signal processors, DSP processors, those are nothing but multiply and accumulate processors. The processor's fundamental thing is multiply and accumulation. And this formulation, they can correlate. This looks like, FIR filtering. I'll talk about it later. So essentially what we are seeing here, we are seeing there are inputs x1 to xn and some weights have been given. Those are multiplied, added, and a biasing factor is added also, and a certain, that z is computed, right? So if you look at it, this expression z, or in USA called z, this expression is analogous to FIR filtering, finite impulse response filtering. In DSP world, or signal processing world, two types of filtering over there. Actually, there are three types, but mainly, uh, FIR filtering and finite impulse response, and IIR, infinite impulse response. But in the practical sense, to compute it with the digital system, we always use FIR filtering. So this neuron, essentially, based on certain inputs, and based on the weightage, and weight comes from the experience. That is the intuition factor is coming over here. We compute this value z, then we normalize it. And that normalization happens using an activation function. I'm not going into detail of that activation function. That activation function essentially maps those input x1 to xn to a single number, a real number between 0 to 1. And in this, over here in this lecture, I'm just using this sigmoid function as an activation function. So it need not be sigmoid function. It can be any other function, normalization technique, right? Depending upon your application. If you are applying into the communication field, activation can be different. If you are applying in imaging, activation function can be different. If you are applying in audio or speech, activation function will be different. If you are applying in the text or other kind of data, for example, banking, insurance, etc., those numerical data. So depending upon the applications, you choose your own activation functions. So this is the fundamental of a neuron. So this is the theory of the neuron. Essentially, neuron is a mathematical function, and that function looks like this. It is analogous to an FIR filtering. Then that output you run to an activation function, it generates a single real number. Okay, out of those many inputs, one number, one neuron generates one output, single output. That output is nothing but a number, okay, between 0 to 1. That's what neuron does. So this is the mathematical model of neuron. Now, as I said, human brain, we have billions of such neurons, right? So similarly, we can put billions of such neurons into the computing. Okay. Let's say, for example, input x1 to xn, we call it input. And there are many, many neurons above there. Those circles you are seeing, each one of them is a neuron. So all these inputs x1 to xn is going to one neuron generating one output, another neuron generating another output, another neuron generating another output. And whenever it is being connected to a neuron, there are various types of weightage factors, and those weightage factors are developed or generated based on certain criteria of the application. So those neurons, will fire. Neuron fire means after taking the input, neuron will generate, series of numbers, and those numbers are real number between 0 to 1. So this input, we call it the input layer, and first level, the neurons are being firing, we call it the layer 1. The output of the layer 1 can go to another, series of neurons that can be layer 2. From layer 2, it can go to another series of neurons, layer 3, like that. Many, many layers are possible. Finally, when it converges, as per desired result, outcome we want to achieve, we get the output y1 to yn. So essentially, there is an input layer, there is an output layer. In between input and output, there are many, many layers of series of neurons. Those are called hidden layers, right? This is the hierarchical, multi-layered, artificial neural network approach. Depending upon how many hidden layers are there, there can be one, there can be two, there could be thousands, right? So that defines the depth of the neural network. Okay. So deep means many such hidden layers. So that's why it is called deep learning. So if there are very deep, artificial, intelligence people or people who develop, they say we have a very, very deep network. Deep network means many, many such, hidden layers. We do not have so much deep, maybe less number of, layers. And so it could be shallow learning also, only few, layers, right? So how deep is the deep? That depends upon how many such hidden layers are there. So this is the fundamentally the concept of the deep learning techniques. Now there are many theories behind it. I'm not going over there. And based on this fundamental concept, all these deep learning frameworks have been developed. You hear Kafka, you hear Yellow, you hear so many things. Essentially, this is what is done over there, right? This is the fundamental. So essentially, this deep learning is learning hierarchical representation of features. What does it mean? So I have some input. I don't know what is that input all about. What is the meaning of that input? I send it to layer 1. I get some information. In computer science or in image processing world or video processing world or audio speech processing world, called features. Then we got certain features, not enough. We take those output, send to another layer, we get little bit of advanced features. May not be enough. We send to the another layer, we get little bit more advanced features, may not be enough. So we keep on sending to many, many layers until it is satisfactory to the user or to the application. So let me give an example. Since I work on image and video processing, I'm just taking an imaging example. Image, any digital image, that is nothing but two-dimensional array of pixels. Pixels means picture elements, right? So there are many, many pixels. And what is in that image? We don't know, right? How do we see? So if we take those pixels and let's say we run through the first layer of the neural network, we might get certain edges like this. I'm just giving a uh, hypothetical example here. We might see certain edges, right? So that means analyzing those pixels through the first layer, edges are highlighted. Edge is an image feature, right? Then I take those pixels and these edges output pass to the second layer. Maybe some object parts are being highlighted. Maybe eyes, parts of the eyes, nose, etc. Then sending the same output to another layer, maybe the faces are visible. Third layer, more like objects. So first layer, it might be edges. Second layer might be parts of the objects. Third layer might be the complete object. So this is the way the feature extraction happens. Feature extraction. So essentially, by using the deep learning technique, we are extracting the features. And based on those features, we can detect objects, right? So that is very, very important in our domain. So convolution neural network, I have to tell a little bit more about it. As I said, convolution neural network, that is today heavily used for the deep learning techniques. There are many, many, with deep learning techniques, but this became very popular. CNN, everybody talks about it, convolution neural network. This actually came study of cat's visual cortex. A cat's visual cortex. Based on the study, it came. How the cat's eye or visual system react. Which parts of the brain or cortex region recognize which type of images or which type sub parts of the images. So it is very interesting. If I ask you, when I'm seeing you, are you seeing the same thing? When I am seeing a cat, I know how the cat looks like. When I'm seeing a dog, I know how the dog looks like. But do you know, when cat is seeing me, what he is seeing or she is seeing? Or when dog is looking at human being, actually what he or she is seeing? It's a very interesting question to ask. And then in case of color, I'm a color scientist. Color is an important aspect. There are three fundamental colors: red, green, and blue. But composition of red, green, and blue, you can generate millions of colors. Then the question I asked, I was giving a lecture in Europe. I asked them, today we have the communication. Today we have the cell phone, the telephony, etc. 500 years ago, there was no telephony. Or 1,000 years ago, there was no vehicle, or there was no airplane, or there was no ship 2,000 years ago. Then how people used to communicate from one part of the world to the another part? Think about it. For example, sky is blue. If you ask somebody in the Africa, they recognize this color is blue. Somebody in Bangalore recognized 2,000 years ago or 5,000 years ago, the sky is blue, color is blue. Or our blood, it is red. So unanimously, although one part of the world is talking to the another part of the world, but what is the democratic system that everybody concluded that is blue, this is red, and that is green? Something to ponder about. Okay, very interesting thing. So these kind of questions often scientists ask, So convolution neural network, actually, it was influenced by the study of the cat's visual cortex. Into the visual cortex, visual system, which parts of the cells or what complex arrangement of the cells into the visual cortex help to recognize or detect the subparts of an image, which are called the receptive fields. For example, human being, we have two types of cells, rod cell and cone cell. The rod cells helps us to recognize the image features like shape, age, depth, etc. But the cone cells that helps us to perceive the color of the region, right? How they work together. So that was the study, and that influenced the convolution neural network. I just wanted to, give you this background. In the papers, you read those papers and all these things, although most of the papers are toilet papers, junk papers, not useful, but you do not get these informations, right? So that's why I wanted to talk about it, to motivate you where from it is coming. Now let's talk about this image. I took a input, 28. I talked to many people, many professors also. Students, I don't blame them. I asked them, so you are doing the convolution, then you do pooling. What is this pooling all about? I do not get a convincing answer. Why you need to do the pooling? I don't get a convincing answer. You already done the FIR filtering. Why after that? So that's why I thought I should talk about it. What is actually fundamentally what it is. Mind it. All these things came from that day, those days, Turing machine and Shannon's theory of communication. Then Nyquist gave the theory of subsampling, Nyquist theorem. You signal processing guys, you work on it all the time, right? Nothing is void of those fundamentals. From those fundamental things, today this thing came, but terminology might be different. I'm helping you to correlate with those fundamental techniques. So essentially, if you have an input 28 by 28, you do the convolution. Convolution means, a two-dimensional filter. You are rotating, convolving the two-dimensional filter, sliding the two-dimensional filter across entire image. Let's say for the sake of argument, the size of the two-dimensional filter is 5 by 5, 5 cross 5, right? There is something called concept of stride. I'm not going in detail over here. Based on that stride, there are 4 such feature maps came out. So if I have a stride 5, 4 feature maps came. And each feature map size 24 by 24. So input size is 28 by 28. Now feature map size is 24 by 24. That means data is growing. And in the digital computing, if data exponentially grow, you cannot handle it. That's why we need to reduce the data. And one way of reducing data is doing the subsampling. Nyquist theorem, subsampling. Or, computer scientists call it interpolation, downsizing, right? That downsizing is essentially called pooling. And what is this pooling? Essentially, it is nothing but redundancy reduction. What does redundancy reduction mean? Where from is it coming? Neighboring pixels are correlated to each other. If you take an image, if you drop every alternate row and column, it will be a smaller image. But you should be able to recognize, looking into that image, this is Dr.Tinku Acharya, or this is Sanjeev, or this is Professor Ganeshan, etc. Right? So that means there are redundant information. Those redundant information are not required. Even if I throw out those redundant information, still I can recognize, I can detect, right? So in convolution neural network, deep learning field, after doing the feature extraction, we apply this pooling technique, and pooling is nothing but subsampling. There are many techniques of subsampling, and that subsampling is the fundamental motivation behind the subsampling is reduction of the redundancy. So I'm going to throw out unnecessary data, Bhagavan Sri Ramakrishna said, you have the milk and Paramahamsa, those, great people. From the milk, they can extract the original, white part, and the water will remain there. So that water is the redundancy, and the parts, white parts, the milk, the real extraction. That means I am maintaining the information, throwing away the redundancy. So that's what happens. So after doing that in the first layer, you got, maybe layer one, 412 by 12. Now first you got, doing the convolution 24 by 24. Then I do the 1:2 subsampling, 12 by 12. So that 412 by 12 is comparable to 28 by 28 original image. That means I did not let data to grow than the input. Then you do the another layer, you get 12 4 by 4 feature maps. Then you do another layer. In this particular example, you got 26 1 by 1. Okay. So, and 26 1 by 1 means 26, a vector of size 26 of 1 by 1 is a real values. You remember in the neuron definition I have shown you, the after activation function essentially generates a value between 0 to 1. That is in the deep learning world or convolutional neural network world called modeling. The programmers and students that are, oh, we have applied this Kafka or this or that framework, and this is the model file. So essentially doing all these things, you generate the, this output that can be used as the modeling. So just example of, pooling, I thought let me explain a little further. So after doing the filtering, you got the filtered data. Let's say the filtered data is size 8 by 8. Now you take the 2 by 2, region, and you take the maximum. For example, this red region, red 2 by 2 pixels. If you take maximum of those 4 pixels, that is 58. If you look at the blue, maximum of those 4 pixels, that is value 32. If you take green, maximum of those 51, and the yellow maximum is 20, 36. So if you create that output, that is called max pooling. So that's why the max pooling concept came. If you take the mean, MEN, mean value, then it can be called mean pooling. If you do median pooling, you can apply any other technique, redundancy reduction techniques, subsampling technique. So you can design your own pooling techniques also. So this is what I try to impress upon you. What is neuron? What is artificial neural network? How the hidden layers come into the story, and because of the hidden layers and multi-layer object extraction, feature extraction, why it is called deep learning, and to do the achieve the deep learning, convolutional neural network, and where it was motivated from the cat's eye, the convolutional neural network came. And in convolutional neural network, essentially what we do, I have explained that, and to do that, not to to stop the exponential growth of the data, we do the pooling technique that also I explained. So this is the fundamental little bit of background of artificial neural network and deep learning technology today. As I said, this artificial neural network is going on since 50s, right? Then this deep learning technique came in 1979, convolution, or I'm sorry, the neocognition theory. After that, so that means more than 5 decades, this research is going on. But it became practical today because of the advent of the computing. I remember when I was first computer I used, in early 80, that was IBM 1130. And that IBM 1130, to run a small sorting algorithm, it might take several hours. And the primary memory was only 16 kilobyte. People are talking about gigabytes today, right? So that time it was not possible to run all these things. Then, computing evolved. In your computer architecture course, your professors must have taught it. CPU, Central Processing Unit, and inside CPU, there are fundamentally three units. One is called arithmetic and logic unit. There's a control unit. There's a memory or IO unit, right? So today people are talking about multi-core computer, Xeon processor, 4-core Xeon processor. What does it mean? There are 4 cores, 4 arithmetic logic units are working parallel. So instead of 4, if you have many such arithmetic logic units, or in simple language, processing elements, that is called GPU. GPU terminology was coined based on graphical processing unit. In the 90s, when I was in Intel Corporation, that time rendering the images on the computer screen, a special type of chip was required for the rendering, so that image can be found on the screen. And for the it was a rendering device. So it did not do any computation. It just used to take the data from the memory or CPU, and in a particular fashion, very fast manner, it used to throw the data on the screen. Right? That was the function. But today, later it evolved. Even into the rendering device, some local computation is possible. So that means those are not just for the purpose of rendering. You can do some processing also. Okay. So that's why in today's world, GPU is called general purpose GPU. That means it is not just graphical processing unit. It's general purpose GPU. That means in addition to the graphical processing, you can do certain computation also. And this GPU became very much suitable for AI. And why? Because you must have appreciated when I was giving the example of the neural network and multiple such layers, so many neurons are working in parallel. So each and every neuron, you can assume a processing element. And what processing they are doing, I have shown into the mathematical function, right? So many neurons are working in parallel. That means so many processing elements are processing in parallel, and you have to feed the data accordingly. So huge data crunching is required. For this huge data crunching, new paradigm came that is called SIMT, single instruction, multiple thread. Even 20 years ago, people didn't know about it. We didn't know about it. This is a recent terminology, multi-threading. 15 years ago, programmers didn't know what is called single threading or multi-threading. Today, people are talking about multi-threading. And that happened because of the multi-core computing. And today, GPU. So, what is the relevance of GPU to the computing? So, GPU contains multiple SIMD units. Talking about SIMD, in your computer architecture class, you have learned there are fundamentally 4 models. One is called SISD, single instruction, single data. Then SIMD, single instruction, multiple data. MISD, MIMD. New paradigm came, which is SIMT. To explain that, I am taking this example. So each block is essentially nothing but a SIMD unit. Single instruction, multiple data. If you look at those neurons in every layer, those neurons are multiple data is coming, but it is doing the same computation in parallel. That is called SIMD. Now, if there are multiple such SIMD units are working together, then it can compute a huge volume of data. So each SIMD, it is computing a vector. So SIMD in computing architecture world, people call vector computing also, vector machine. So essentially each vector is a thread, and multiple such threads are happening in parallel. So single instruction, multiple thread. Because of the SIMT, multi-core or GPU-based computing became very parallel, very popular and very effective. And because of this, artificial intelligence or deep learning techniques are possible today. Even your data can be in the cloud. Even in the cloud, you can, in the data center, use processing elements over there. You can take those data, you can process over there and send out. That is happening because of the advent of the computing, because of the advent of the multi-core computing, because of the advent of the low-power VLSI signal processing, because of the low-power VLSI architecture design, and on top of that, paradigm shift into the computing programming model, SIMT. That's why artificial intelligence or deep learning became popular today. Look at this particular video. I saw this in one of the, conference in United States 3 years ago. I was there for a couple of hours. So this particular machine is playing against a human being. In 2 hours, no human being, these are all expert players, could beat this machine, right? This machine can predict, can make the decision, what is the trajectory of the ball, and the opponent body language, the posture, and do everything and can play, right? So this is AI and IoT machine. So I have talked about AI. With this video introduction, let me talk about IoT. This is a very interesting thing. These days, everywhere I hear IoT, but lots of misconception about IoT. What is IoT all about? I like to break the misconception today. So if you look at the evolution, internet evolution, early 80s, it was internet of documents. Documents used to be through the network. Documents can be sent from one place to another. Then internet of commerce, banking, insurance, those adopted that. Documents can be email. Through email you can send those things. Then it became internet of applications. Internet of application means there is a computer in one place and multiple people through the terminals, they can run various kinds of applications through the networking. Then became internet of people. What we see today, that is internet of people. That means over this online, I am talking to you, audience. I am not talking to any machine. I am communicating with you, people. Over the cell phone, we talk to people. When we send an email, we send to people. When we send the social media, when we send the messages, we are communicating with people. So internet of people. Already internet of things started, and future is internet of things. That means internet of things, devices, in addition to people. Devices will be talking to each other. Devices will be communicating to each other automatically without human intervention. Driverless vehicle is a classic example today. So essentially, if you look at the evolution, this is the evolution. And what is this Internet of Things anyway? If you look at it, what is happening worldwide at this moment in 60 seconds? Just now, if you start 60 seconds, what is happening? More than 168 million emails are sent. More than 700,000 search queries are happening. This is little dated data. These days it is even more. More than 600 news video popping up. So many calls are happening. Millions and millions of calls are happening. So huge volume of data is generated in 60 seconds. As a result, approximately 20 quintillion bytes of data generated every day today. 20 quintillion means 20 multiplied by 10 to the power 18. And what kind of data? It could be structured data, it could be unstructured data. Unstructured data means, multimedia data is unstructured data. Image, video, speech, audio, these are all unstructured data. So lots of data is being generated. So how do you transmit those data? How do you shape those data? How do you process those data? Very, very important. And if you look at, each and everything, today, which you are seeing, watch, smart watch, the refrigerator machine, these IP, CCTV camera, even your credit card, these are all became sensors. These sensors connected to the internet or network can generate and transmit the data. These all are IoT devices. Each and every one of you are carrying IoT devices, right? So what is this IoT all about? Kevin Aston, he first gave the concept of IoT in 1999, Internet of Things. And the things is later, the scientists like me gave the complicated, definition. Inflexible mixture of hardware, software, data, and service collectively called objects. So you figure out the meaning. Inextricable mixture of hardware, software, data, and service collectively called objects. So those objects are things. And when those things are connected to the internet and generate data, process the data, transmit the data, that paradigm is called Internet of Things. So essentially, Internet of Things is the network of physical objects. Physical objects means it could be human being, it could be animal, it could be your car, it could be your house, it could be your devices, anything physical. Can be animate object, can be inanimate object. Devices, vehicles, buildings, animals, people, any other item embedded with electronics. And that electronics is processed to a software. And the sensor data processed to the software, generate information. And then the data is transmitted to the network connectivity. That is the formal definition of Internet of Things. So essentially, anything under the sun which is embedded with electronics. By electronics, I mean the sensors that generate data, has the capability of transmitting the data from one location to another location, from one device to another device, from one person to another person. That is Internet of Things. Various people, use various terminologies. Machine learning people, they say machine to machine, machine another end of the world. So it is nothing but a virtually world-size web. And in the Terminator movie, they use the concept of Skynet, and that was also Internet of Things. So it is the concept is same, and the concept I already explained. So if you look at the ultimate goal, as I said, today it is people, tomorrow things will be communicating with each other. Now the question is, so if we do it right, if it is done by half-educated people, non-experts, it can pose a danger. But if it is done properly by the experts, well understood, it can create lots of opportunities. I am skeptic. So that's why I say, if understood and truly secure, security is a very, very important thing, particularly today's world of cybersecurity. IoT can enhance communication, lifestyle, and delivery of services. It has fantastic applications into medicine, fantastic applications into the surgery, fantastic application in the delivery system, many services. But if misunderstood, if not done properly, and if it is done by half-educated people without understanding the entire gamut, it can pose the threat to data privacy, safety, and life. Think about it. People are talking about driverless cars. Each vehicle, it has many, many sensors embedded into that vehicle. Those sensors are instantaneously generating the data, sending to the cloud. From the cloud, instruction is coming. And cloud is detecting, some unforeseen thing is detecting, which direction vehicle will go, which speed vehicle will go, etc., etc. Now think about it. If cybersecurity happens, if the security measures is not taken properly, if the corner cases are not taken care of properly into the programming or design or into the device, and every car in city of Bangalore started driving randomly in 100 kilometers per hour, what will happen? That will become worse than a nuclear war. Okay, so that's why I always talk about it. Information security is very, very important. And when we are developing the IoT, we have to make sure that proper protocols are applied. So this is little bit of IoT. Now, time is short. I like to finish in 10 minutes. Usually I give, day-long lecture on video analytics because video IoT, I coined the term video IoT, number of years ago with Intel Corporation. So earlier it was just IoT. I call it video IoT. And video IoT became popular because of the video analytics. Now the question is, what is video analytics? So this is a, sculpture of David. And this is the most beautiful sculpture one can ever see in this world. And this was designed by Michelangelo. This is the perfection, perfect art. So Michelangelo said that I saw the angel in the marble and carved until I set him free. That means a one piece of stone cutting out the unnecessary portion. This, it was not that hand was made and head was made and leg was made and put it together, glued together. It is not like that. Carving the stone, this David came out. So video analytics is the same thing. Essentially, we have huge volume of video data, and from this huge volume of video data, extracting the meaningful information. Okay, meaningful information has to be actionable. That means I can extract the information. Where from information is coming? From the video data. Where from video data is coming? From the video camera. So from video camera to the network, I'm gathering the data, I'm analyzing it, extracting the meaningful information, then actionable information I'm sending network to some other place. That is the fundamental concept of video analytics. Question is, why we need to indigenously develop technology in India? Talking about video analytics, I hear sometimes unattended object. So morning 6 o'clock, this is a railway platform in Europe, right? If somebody leaves an object over there, it is easy to identify. But if somebody leaves an object, morning 6 o'clock, I took the picture, in Howrah station. So do you think object can be identified? Difficult. For example, in Japan, somebody left that bag. So it is very easy. It does not require a rocket scientist or big engineering colleges to develop the technology. Even high school kids can develop that. This is a bag and this man leaving the bag, automatically detecting that. This is the city of Lucknow, Lucknow street. Somebody left that bag and walking away. So just dumping the foreign technologies and bringing in our environment not going to work. So India is different. Our demographic condition is different. Our cultural condition is different. Our weather condition is different. So we have to develop the technology, particularly in the domain of video and imaging, and also in the medicine, right? Suitable for our own demographic conditions. That's why indigenous technology development is very, very important. For example, traffic. My home in Arizona, just outside my home, this is the traffic pattern. This is the highway. And this is in Kolkata, traffic pattern. This is in Delhi. Do you think the traffic management bringing from the foreign country and dumping over here is going to work? It is not going to work. People talk about radar. Radar does not work in India. Using the radar, I'll be doing, on the street, if you see the police is using a radar gun and telling you you are driving 80 kilometers per hour, you should challenge them because that is not accurate. Using the Doppler effect, radar technology works based on Doppler effect. Electromagnetic signal is going. And the Doppler effect, it varies. If you know about the Doppler effect, you engineers should know about it. Depending upon the density of the media. And what is the media here? Media is the air. So in winter, media is one density. Summer, media is one density. After rain, it is another density. Lot of scattering. Then line of sight. If somebody is taking that radar from the side of the road, then there is something called cosine. Cosine error is there. So lots of error happens, right? So video is the way to go, and lot of technologies can be developed. For the sake of our nation, we need to indigenously develop the technology, not just dumping those technologies from the foreign countries, bringing those radars, bringing this, bringing that. We are only making foreign countries rich, not us. So we have to develop our own video-based technologies. So last 15 years, I am doing this R&D in my R&D organization, Videonetics. Some of the applications which we have developed, I cannot show, more than 110 applications has been developed. I'll show few in a couple of slides. Please watch it. While you are watching it, let me take a rest to my throat. So let me shorten it. So essentially what I have shown you, CCTV cameras are all over the places. So CCTV camera is not just looking into the thieves or thugs or etc. It is not just for security. It can be used to keep our cities clean also. If we develop the algorithms, particularly today's the world of deep learning and etc. The same CCTV camera which has been installed, it can be used if the garbage bin is overflowing. Then immediately it can send a trigger using the IoT. The camera becomes the IoT device. It sends a trigger that garbage bin is overflowing, please clean it. The moment it is cleaned, another trigger will happen. It has been cleaned. That means between when the garbage bin was overflowing and when it is cleaned, what is the duration? That means how long it took to clean that garbage can. So this data information can give lots of information to the concerned authorities so that they can enhance the operation. So when we say smart city means, enhancing our lives, enhancing our living conditions. So that is the purpose of the smart city. So that's why I have shown you that video, and it has been installed, demonstrated and under installation in Chennai. How it can be used as a investigation? Look at it. I see a bag over there. Question is, who left that bag? After searching all the cameras in the neighborhood, pointed out automatically, this is the person. Now, who is that person? Again, searching all the cameras based on the attributes of the person, the dress wearing, height, width, everything. These are the possible suspects. Then do the critical review. This is the suspect. He was wearing a mask. So this is the person. So that's the way, this video IoT or video analytics based on these artificial intelligence techniques can be used for the forensics also. It can be used in the intelligent traffic management applications, for example, automatically detecting, using the normal security cameras. We don't have to put police every 50 meters, every intersection. Security cameras can detect, which are the people not wearing seat belt, right? If it is green, it is wearing seat belt. If it is not wearing seat belt, red alert will come. Such and such vehicle, such and such person did not wear the seat belt. This is the license plate number, can be warned. Similarly, people not wearing helmet automatically can be detected, or more than two people, riding on the motorbike. That is dangerous. That is against the law. Called triple riding can be automatically detected, and challan can be generated, or warning can be given, right, based on the evidence, image, time stamp, etc. People, we often see, it's a dangerous thing. People are talking about the cell phone and driving on the busy road. That can be detected. And let me show you a case study in Anna Nagar, which has been deployed in Chennai, Anna Nagar traffic management. Real life case study. So technology, has been deployed. Traffic becomes smooth, and no more manual. It is happening automatically happening. So 140 CPs, adopted these AI-based technologies. 80 airports in the country, and lots of success stories over there. Let me stop here. And time is short. Maybe I have 5-6 minutes to take a couple of questions, if any. Thank you very much.
Thank you very much, Dr. Acharya, for this very interesting and useful introductory lecture on fundamentals of artificial intelligence and the way in which you transition from AI to IoT and IoT to video IoT, and then finally talking about some specific use cases that your company has developed. So please, I request all the audience members to join me in virtually thanking the speaker for his time and the wonderful talk. So I now request the audience members to post their questions on the chat box. I see that there are 1 or 2 questions already posted here. Otherwise, you can also directly unmute yourselves and then ask the question. There are a few hands raised here. So before handing it over to the participants for the direct question, let me read out one question from the chat box. This is by Dr. Ganesan. It says, Dear Dr. Acharya, thank you for an enlightening talk. In the video analytics that you showed, are you making an algorithm for a specific task, focusing on one area or object and ignoring the rest? Or multiple algorithms are running in parallel on the same data, which is tuned for specific tasks of recognition?
Very, very important question, and it's a loaded question and very relevant question. Yes. So essentially, when the early days, let me give little history. Early days of analytics, for each object, single algorithm was developed. Only that object can be detected, etc., etc. But the way we have developed it, it's more like a generalized framework. So various types of objects in parallel can be detected using the same neural network. Okay, it is possible. So most of the neural network, if not all, they're targeted from one object, one type of object. They train with one type of objects only. But we have developed, we have invented, we have filed US and Israeli patents on that. We have developed a neural network technique, and I'm not going into the detail, by which multiple types of objects. Now, when I say multiple, is all types of objects? The answer is no. That is not a truthful statement. We identify, let's say, these 10 or 15 types of objects will be detected in parallel. So that means in the scene, there is two people, 10 cows, one dog, 3 vehicles, one a four-wheeler, one two-wheeler, one auto rickshaw, one thela, one truck, that kind of thing, right? So you can do that.
Okay, I see that Subodh has raised his hand. Perhaps he has a question.
Yes. Dr. Acharya, thank you so much. I work for Cisco, and we have been privileged to partner with you. Especially, we had a preview of the Deeper Lock, the DL platform which you have, and it's simply wonderful. I had a few questions around data privacy and ownerships when you look at video and AI analytics on the cloud, and just your broad comments and what are some of the areas, especially in the context of who owns the data captured from a CCTV camera, and especially when the solution is cloud hosted, and how do you hand off and normalize and ensure data and privacy rights are maintained in this? Any thoughts or high level comments on that?
Subodh, fantastic question. You know where the problem lies? Problem lies from the camera itself, right? So, India is a very interesting country. I love this country, because we are in the L1 game, no? So in the L1 game, we get all these cheap Chinese things, put it over there, then everything comes on Cisco. Okay, through your network, all the data is being leaked.
Right.
I understand your pain. Similarly, all the problems will come to the software. Oh, okay, network, blah, blah, blah. Problem starts from there, the sensory device. As I said in the IoT, the camera sensor itself is a sensory device. So what kind of protocol I can put over there so data cannot be stolen? That is one thing, one way. Another way, let's say for the sake of argument, data being captured from the camera is being secured. Now it is coming to your server, to the network. What can you do over there? I'll tell you a couple of eye-opening things. Anybody who has a Mac machine, have you ever been hacked?
Not really.
Anybody who is using Linux, have you been hacked? Not really. So essentially, when the hackers hack, what is the most vulnerable point? They hack to the web and they hack to the operating system. So that's why devices and software has to be developed OS agnostic way. India is the land of technocoolies. Okay, we do not develop any product. In the land of technocoolies, what is the shortest possible time we can put a software together, right? And people don't pay attention. What is the implication behind it? And shortest time to do that thing, what we do? We utilize the OS intrinsics. We utilize ActiveX. We utilize the media, module. We utilize these. Those are freely available. Those freely available things, which is available in the operating system, and we develop the technology. That is the vulnerable point. So in my lab, the guiding principle was, we are not going to use any operating system. I need the machine as a bare metal. And OS simple kernel is required to wake up the machine. We are not going to use any OS intrinsics. That's the reason 6 years I have invested millions. Make sure it is OS agnostic. Same thing will work, doesn't matter what operating system you are using, I'm not going to name them, including into the virtual environment. That is another way to protect, and has to be browser agnostic. That means you are not using those browser intrinsics either. If few measures you take to some extent, you'll be able to save yourself from the security attack. On top of that, yes, in the networking environment, router and all these things, in situ, lot of computations can be done. By doing the in situ computation, you can frustrate the attackers. After saying so, since we are talking about digital computing, and we are talking about the algorithms, and these are all deterministic. If a smart hacker, some software might take to break one day, some software it might take to break 50 years, depending upon what protocol you're taking. But you cannot guarantee it can never be broken. Same thing in the cryptography, right? It is deterministic in nature. Okay, so when you put the encryption, you put a supercomputer, try for 50 years, you might break it, you'll get the password. So deterministic, nothing is 100% proof. But when you are developing the technology, deploying the technology, if you are aware of it, where are the vulnerable points, you can take proper actions. I hope I could answer you, Suat.
Absolutely, Dr. Acharya. It cut a wide swath, and I think you linked it very nicely. And just a little follow-up. Whenever I'll surely reach out to you, but I'm really interested more on the deeper look approach, because we also use a mind meld workbench approach inside Cisco for video IoT, and very, very keen to just get more insights. Thank you so much for sharing your insights.
Yeah. Please, contact me. We'll be happy to exchange.
Sure. Thank you so much.
Our intellectual thoughts.
Yeah, absolutely.
So bottom line is, what I'm promoting over here, don't be dependent on one particular operating system. Don't be dependent on one particular. If somebody comes and tells you, without installing this OS, your system will not work, throw those technology out. You should be saying, I want to be agnostic. That will solve 90% of your cybersecurity problem. Cisco. Since Cisco Sumad is here, and I have a long association with Cisco, I had a fantastic chat, 15 years ago with Howard Charney. Howard Charney was one of your board members, and he was the head of the division. So Howard and I had a long chat, and we conversed to this concept that we need to be away from the operating system dependency. And Cisco follows the same principle. That's why almost all your systems are in Linux.
Yes. And we are seeing that for 5G, especially 4G to 5G migration and everything around SASE and zero trust architectures.
I propose that when your Amit Fadnis over there, that's what I begged him. Amit, please do not be dependent on any. Amit Fadnis is not in Cisco anymore.
Yeah.
Cisco India head. When I was in Bangalore in your office, I had 3 days brainstorming session. That's why I told them, beyond Linux and they just kernel, don't use anything.
Absolutely. And we heard you that time. Thank you so much, Dr. Acharya. Really, really.
Thank you.
I won't take much of your time. Thank you so much. Thank you, Sanjeev.
I'll take one more questions because I have another meeting to attend.
If there is any, maybe one other very quick question, you can take it. Otherwise, we can directly go to vote of thanks.
I'll ask that question. So if you can give details about the network what you are using in your analytics. I mean, you don't have to give the full details. Maybe you can say what type of CNN or what type of network that you are using, where you are training for the multiple tasks in one network.
We have developed our own network, as I said.
Okay.
Using Kafka, YOLO, those kind of things, you can achieve at most 70 to 80% level. I'm not telling all those are bad things, very, very good things. But for mission critical applications, you cannot depend on, for example, if you want to do your ANPR, you want to recognize the vehicle, right? India is, as I said, I love this country. It's a challenging country. It's a challenging environment, challenging corruption, challenging politicians, challenging bureaucrats, challenging people, challenging road, challenging driving condition. And the research problems are also very challenging. So that's why if technology works over here, it will work anywhere in the world, right? In that challenging environment, in your Bangalore, my technology is running over there, right? How many times you see these trucks or vehicles non-standard license plates? And when it is non-standard, how can you apply ANN? You cannot. But the requirement is I want 98% accuracy. Okay. So and two-wheeler. Two-wheelers are the most nuisance thing, right? Some of the characters are broken. Some of the characters are, so that is the true intelligence. Using normal open source, those models, you cannot go that far. But yes, there are certain applications you can use those models, where maybe that level of accuracy is not required. But when you need that high level of accuracy, when it is mission critical, you have to develop your own network. Period.
Thank you, Dr. Acharya. That's really wonderful talk. I think you took it really from the basics all the way up there. So thank you. Yeah, I will now ask Subodh, please offer the vote of thanks.
Sure. My absolute privilege, and I won't hold you long, Dr. Acharya. Thank you so much from the bottom of my heart on the team of the entire XCOM ComSoc Society Bangalore, for which I'm a member along with Ganesh and Sanjeev. A few of my colleagues are here from Infosys, like Priya is here as well. We cannot thank you enough profusely. If I had to summarize one or two key takeaways, I would always say the way you emphasize on causation and correlation was phenomenal. It's not just about how things work, but also how they not work. And from an inventor's mindset, the way you explained and linked it to industry use cases, non-standard license plate. We're all working on LPDRs and APDRs, and we all know the challenges. From a practitioner's mindset, you covered all the bases. From an inventor's mindset, you checkmarked everything. I'm simply enraptured. I was blown away the way you simplified it for us. And I'm sure everyone in the audience could relate to something and carry it back. And I think this is the way we can really have scalable, mass scale use cases developed, which fit in India and also globally. Thank you so much for sharing your insights. We're really, really privileged to have you.
Thank you. Thank you very much. Okay. Bye-bye.
Bye-bye.
Dr. Acharya. Bye.
Thank you very much.
Thanks, Anisham. Thanks, Sanjeev. Bye.
Thanks. Bye.
Bye.
Thanks all.
Thanks everyone for joining us.